So, good evening, everyone, and I welcome you all to today's live session. So, week 7. So, I hope that you people have gone through the lectures of week 7 and you people have gone through the necessary concepts that has been taught. And so, I'll be discussing some questions so that it will be helpful for you to solve the assignment problems. So, name of the course is Nonlinear Vibration, NOC24 ME54. And this course is being taught by Professor S.K. Dwivedi from IIT Guwahati. And I'm Rashi Aditi Ranjan. I'm an NPTEL PMRF TA and I'm a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. So first I'll be talking about some overview of what has been taught. So if you people remember, so the basic concept that was taught in this week's lecture was for a parametrically excited system. So up till now, whatever we have discussed and whatever problems we have solved, what we have considered is that our system is, when it is forced, it is actually a forced system, okay, or a basically externally excited system. Externally, you are the external force which is being applied on the system. It is actually excited. It is changing with time. And okay, am I audible? I forgot to ask.
Yes, madam.
Okay, thank you. Okay, so like for example, we have the Duffing oscillator, right? So in case of a Duffing oscillator, what do we have? So in case of a Duffing oscillator, what do we have? We have something like x double dot omega n square x plus c x dot and some alpha x cube term. It's equal to f sine omega t. So if you see, this external forcing is actually what the system is excited through, right? It's an external forcing. But if I talk about a parametrically excited system, what it is and how is it actually affecting the system, and what are the physical system that are actually has these kind of a system. Okay, so I'll be covering everything. However, you people must have studied in the lecture also, but I'll try to revisit that. Okay, so and then the resonance theory what was taught, which actually dealt with that how the resonance condition occur in a parametrically excited system. Like in case of a excited system, like in case of a Duffing oscillator, when does the system experiences resonance? It experiences resonance when omega is equals to omega n, right? When the forcing frequency is equal to the natural frequency of the system. But in case of a parametrically excited system, that is not the case. Okay, the system actually experiences resonance far away from that of the natural frequency of the system. And then Floquet theory was taught, and this theory is basically used to know about the stability of a parametrically excited system. So what happens is that in case of a Duffing oscillator, we have already studied. Okay, I have covered it in the live sessions also, that how can we use the concept of Jacobian and finding the eigenvalues to actually know that what is the stability of the system, whether it is stable, whether it is unstable, whether it is marginally stable, whether it is going to show spiraling in behavior, whether it is going to show spiral out behavior. I've already discussed. Okay, but in case of a parametrically excited system, that is not which will be applied. Okay, so we study it through the Floquet theory. In case of a Floquet theory, we use a parametrically excited system. Like for a parametrically excited system, I basically derive the, what do we say, monodromy matrix, and then on the basis of that, we find the stability of the system. Okay, so I'll be talking about these in detail when I'll cover up the questions. Okay. So the first question is, which of the following is not a parametrically excited system? So the first question is that how do I distinguish between a parametrically excited system and a externally excited system, or we say a forced system? Okay, so as the name suggests, parametrically excited system, which means that the system is excited by the parameter. Okay, so whatever the parameter is present in the system, it is actually excited, which means that it varies with time. Okay, so now what is a parameter? So as we have studied also, now we have studied the bifurcation diagram also, and I have covered many questions related to the bifurcation theory. So you people must have understood what a parameter basically means. So as you people remember that in case of a when I was talking about the bifurcation theory, we were actually talking about the buckling of a beam, where there was a mass m, then it was like this kept on a beam, and then there was a big mass capital M, and this led to the buckling of the beam. Okay, so what was this M or capital M? It was a parameter. Okay, so the variation of this parameter actually leads to the variance in the static characteristic of the system. However, this was a static case. Okay, what about a dynamic case? What if my parameter is changing with time? What if this mass is changing with time? Then what is going to happen? I'll just make this in a very small zone so that I can use the further area for explaining the question. Okay, so my M or M is a parameter. Okay, now, so for a parametrically excited system, what happens is that the parameter varies with time. Okay, my parameter varies with time. And in case of a Duffing oscillator, for example, which is a forced system, you see, like for example, here the B option, which is a Duffing oscillator, right? It is not a parametrically excited system. Here, this term f sine omega t, is it a parameter? No, this is not a parameter, because in my case my parameter are those values which are actually multiplied with my response, or maybe the differentiation of the response, or maybe the double differentiation of the response. Whatever coefficient is multiplied with those, we call that as a parameter, right? So in this case, if you see, f sine omega t is not multiplied by x or x dot or x double dot. So this is actually an external forcing that is happening, that is being applied on the system. So this is not the case of a parametrically excited system. This is actually a forced system, and the forcing is sinusoidal in nature. Now, if I talk about option A, if you remember this, which type of equation this is? Okay, anyways, it is our Rayleigh or van der Pol equation. Basically, this is the van der Pol equation. So this is also not a parametrically excited system. Are the parameters being excited? No. Here are three parameters. One is 1, another one is 1, and the third one is 1.5. And all these are constant throughout the response. It does not change with time. They remain constant with time. So this is also not a parametrically excited system, neither it is a forced system. Okay, it is a what? It is a free system. However, limit cycle actually exists in this. However, the limit cycle actually exists in this system. As you remember, if I give a small perturbation to the system, and what happens is that it tries to follow a path, whether the perturbation is outside of that orbit or maybe it is inside of that orbit, this system tends to take the system to follow that particular orbit, and that is known as our limit cycle. Now let us come to the option C. Here if you see, we have x double dot plus pt of x is equals to 0. Now see, this p of t is actually a parameter, which is a function of time. It is an explicit function of time. Okay, so p can be written as something like t square, t cube, sine omega t, like that. Okay, so here this parameter pt is actually varying with time, and hence this is my parametrically excited system. See, we have a x here. This is actually a coefficient of x. Okay, so this is my parametrically excited system, and this is also known as the Hill's equation. Okay, and coming on to the fourth option, what we have is x double dot plus some delta twice of epsilon cos of 2t into x is equals to 0. So if you see here also, the coefficient of x, which is this, is actually dependent on time. I have this delta plus 2 epsilon cos twice of t. This is a periodic function. 2 epsilon cos of 2t is a periodic function plus some constant value. So if I add some constant value inside a periodic function, what is going to happen? So for example, if I have, let us suppose 1 plus cos of t. So what is going to happen? My cos of t varies from -1 to 1, and I've added a 1 into it. So now it will vary from 0 to 2, right? But it will be a periodic function. Okay. So here also, my this parameter, which is multiplied with x, is actually a function of time. Okay. So this also is my parametrically excited system. And this is also known as the Mathieu equation. Now you would be like, what is this Hill's equation? What is Mathieu equation? So if you people remember, we always have an ideal model for every kind of a system that we can encounter. Like for example, we have a Duffing oscillator, right? By which we are able to model the vibration of a system, be it the damped out vibration, be it with an increasing amplitude, be it with a spiraling in, spiraling out, constant periodic motion. We have a Duffing oscillator by which we can actually express that how a nonlinear system which has a forcing behaves. Okay. Likewise, for limit cycles, we have a van der Pol equation or Rayleigh equation by which we can introduce the concept of limit cycle, and it is an ideal system that shows what a limit cycle is. Likewise, for a parametrically excited system, we have these two equations, our Hill's equation and the Mathieu equation. Okay, so these are also our ideal systems by which we'll be able to study that how the parametrically excited system actually behaves. Okay, so answer of this question will be, which of the following is not a parametrically excited system? A and B, because our C and D both are the parametrically excited system. Coming on to question number 2. For a parametrically excited it should be, the resonance occurs at excitation frequency, away from the excitation frequency, none. So for a parametrically excited system, what happens is that, see, in case of a Duffing oscillator, we know if I write plus kx plus cx dot plus alpha x cube is equals to f sine omega t. So what do? We take an analogy. So if you remember that if I take alpha is equals to 0, what will happen? It will become a simple spring mass damper system with a forcing. So if you guys remember that for a linear spring mass damper system, what happens? That kind of a system, when subjected to a periodic forcing, it shows periodic oscillation, that too of frequency omega, because whatever the component which is present in the system, which is due to the natural frequency of the system, it is going to die out because of the presence of the damping. So we are going to have oscillation with that frequency, that of omega, which is the forcing frequency, right? But in case of a parametrically excited system, that is not the case. In case of a parametrically excited system, what happens is that our system actually experiences resonance far away from the natural frequency criteria. Right. So there are three criterias at which resonance can occur in a parametrically excited system. First one is our principal parametric resonance. So what happens in this case is that, for example, my natural frequency of the system is, let's say, 1. If it is a continuous system, there are many modes of frequency, right? How, if you remember that for a spring mass damper system, 1 degree of freedom system, we had only one natural frequency. For a spring mass damper system with 2 degrees of freedom, we had two natural frequency, and likewise for n numbers, we will have n natural frequencies. However, in case of a continuous system, the degree of freedom goes to infinite, and that is why we'll have infinite frequencies. Okay, so we have first the principal parametric resonance. So what happens in this case is that we experience the resonance omega at omega n m plus omega n. Now what is omega n? What is omega n? So these are actually our, okay, no, this will not be the case. This will be actually twice of omega n, where omega n is my nth natural frequency. I can have multiple natural frequencies, right? I can have first natural frequency, second, third, like that for a continuous system. So in that case, this is where my resonance occurs. Second case is my combination parametric resonance. Now this is further divided into two categories. Okay, one is your sum addition type and one is the subtraction type. Okay, sum type and difference type. So one case is my omega m plus omega n, and second case is my omega m minus omega n, where m and n are the two different frequencies. Like for example, for a continuous system, I can have n natural frequencies. So any two, I can pick any two. For example, omega n, and I can pick omega n minus 5, likewise, like that. Any two. So summation of those two and difference of those two. So my resonance can occur at these point also. Okay, but my resonance usually don't occur at omega is equals to omega n. So the answer of this question will be away from the excitation frequency. Okay, like in case of a forced system, why do we find that where is the natural frequency? Because we know that at the natural frequency, our amplitude of vibration is going to be very high, and we want to avoid it because we don't want to get into any kind of a failure into the system. So that is why we avoided. We try to find that where is the natural frequency of the system. And in case of a parametrically excited system, these are the three cases which I have to keep in my mind when I'm dealing with these kind of a system, so that I can avoid any kind of a failure or any kind of instability into the system. Coming on to the third question. which of the following is not a Mathieu equation? So, you know what a Mathieu equation is, and it is important that we know that which of the following can be and cannot be a Mathieu equation. So, this is a very easy question actually. A, it is not a Mathieu equation. B, it is also not a Mathieu equation. Both A and B are what? These are Duffing equations, different type of Duffing equations. And C is my Mathieu equation, I know that. So A and B are my correct answers, right? And this is my Mathieu equation. Also, there's one more thing I would like to mention over here. What if my equation is of this kind? Let us say there is some force F applied. Or maybe we have F sine omega t. Now what is this? I missed a X over here. Now what is this? Is it a Duffing equation? Definitely it is not a Duffing equation. Because in my Duffing equation, my parameters were actually independent of time. My parameters were not changing. They were constant throughout the time. However, my forcing was changing. In this kind of a system, my forcing is also changing with time, but my parameter is also changing with time. So this is also known as the forced Mathieu equation. Okay, this does not comes under the category of a Duffing equation. This is my forced Mathieu equation. A forcing is also applied into the system along with the parametric excitation. So this is a forced Mathieu equation. I hope that this is clear. This was a very easy question. I think now you people will be able to, find the difference between different kind of a systems, isn't it? Like for example, if I say that is this a Hill's equation? If you remember, my Hill's equation was given like this. This was my Hill's equation. If I compare my Hill's equation with my Mathieu equation, like this one, I can see that this, whatever my coefficient is actually a function of time. It is a parameter, it is a function of time. So my Mathieu equation is also a type of a Hill's equation, isn't it? So you people should know that what kind of equations are, what kind of equations are going to show what kind of a behavior. So that whenever you are dealing with a physical system, whenever you are dealing with a physical system whose behavior you don't know and you want to find out that what is going to be the behavior of the system, so by the equation of motion over the behavior you can know that okay, this is how the ideal system behaves, and so this system is behaving like this, so what kind of analysis is needed in the system. Okay, coming on to question number 4. For the equation perturb the system and obtain the new equation. Okay, so the given equation, what is this? Which equation is this? Do people remember which equation is this? This is a Duffing equation. Forced Duffing equation. Right. This is a forced Duffing equation, isn't it? Now, if this is a forced Duffing equation, so if I want to find out that how my system is going to perturb. So by perturb, what do I mean? By perturb, I actually mean is that I will change the system a bit. How am I going to change the system? So if you remember that when we were dealing with the stability of a system, how we were actually finding the stability? We were actually giving some disturbance to the system, isn't it? So if I'm giving some kind of a disturbance to the system, what is going to happen? If I'm giving some kind of a disturbance to the system is either going to come back or it is going to go far away. That is what is going to happen, isn't it? Either it is going to come back or it is going to go far away from itself. So then how is the system behaving? Okay, so see, if you see this equation, what is happening? There is a forcing present and there is a damping present and there is a nonlinearity as well. So firstly, if I want to know that what would be the solution of this system, what could be x for a forcing of f sine omega t, what could be x? So now intuitively I can say after studying various kind of processes that my x is going to be periodic. In an ideal case, although the solution of x can be written in form of a Fourier series, it can have many components of omega, and but I can consider that it is like a periodic function. I can consider for some values of parameter, it is going to show a periodic behavior. If you remember what we were doing in the method of multiple scale, what we were doing in the method of harmonic balance, we can have a x is a periodic solution. X is my periodic. So if my x is periodic, then now I have to give it a perturbation. Perturbation means from whatever path it is following, I'm going to just take it from there and keep it from a very small distance difference. Okay, then what is going to happen? So I can write my x, let us suppose I have a new solution. So let us suppose that x naught is the periodic solution. So I can write some random y is equals to x naught plus, let us say, what variable can I use? Z. Let us suppose Z. This is my periodic solution and this Z is some perturbation from x naught. Okay, so if it is perturbing by x naught, then what is happening? If now I want to put this in the main equation, for that I'll have to find out the differentiations, first differential, second differential. So what am I going to do? I'm going to find y naught, which will be equal to x naught dot plus z dot, correct? And I'll have to find y double dot, which is going to be x naught double dot plus z double dot. These will be my differentiations. Now coming on to other terms, if I have, so I also have a x cube. So if I want to find y cube, so what I'll be doing is I'll replace, to find the perturbed equation, I'll replace my x by y, where my y is given like this. Okay. Now if I want to find y cube, so I'll have x naught plus z whole cube. Now, if you people remember, as I mentioned, this z is very small. Okay, I'm giving a very small perturbation, very small deviation from the actual behavior. Very small difference. Okay, so if I'm giving a very small difference, then I can neglect the higher powers of this z. For example, if my z is, let us suppose 0.01. So what is going to be the power of 0.01 to the power 3? So we have 10 to the power minus 2 to the power 3. We'll have 10 to the power minus 6. That 10 to the power minus 6 have any significant contribution into the equation of motion? Definitely not. As compared to 10 to the power minus 2, 10 to the power minus 6 is a very small quantity. So I can neglect the higher terms, higher power terms of z. So if I write this, it will be x naught cube plus z cube plus 3 x naught z square. I neglecting the higher power of z. What am I going to get? I'm going to get this as x naught cube plus z cube plus, oh sorry, z cube, so I have to neglect 3 x naught square z. This is what I'm going to get. Now I'll put it in the main equation of motion and see what is happening to the system. Okay, I'll try to write it here only. So my main equation of motion is this. Now if I put this in the main equation of motion, what am I going to get? I'm going to get x naught double dot plus z double dot plus omega n square x naught plus omega n square z plus 2 zeta x naught dot plus 2 zeta z dot plus beta x naught cube plus 3 beta x naught square z is equals to f sine omega t. So this is the new solution that I got. Now if you see, as I have written, that x naught is a periodic solution. If my x naught is a solution, what does it mean? For a differential equation, if I have a solution, then it means that that differential equation is always going to satisfy the solution, right? So if my x naught is a solution, then the force stuffing equation that has been given in the question, x naught is going to satisfy that equation, right? So since x naught satisfies the given equation, we have, what do we have? I'll write in the next slide. What do I have? I have x naught double dot plus omega n square x naught plus 2 plus beta x naught cube is equals to f sine omega t. This is always going to be satisfied, okay, for x naught. So if this is satisfied and this is my equation, let us suppose this is equation 1 and this is my equation 2, what is going to happen? If I put from here, I have a value of f sine omega t, right? If I put it over here, then you'll see that all these terms are going to get cancelled. All the x naught terms are going to get cancelled. So if these terms are going to get cancelled, what is the new equation of motion that I get? So the new equation of motion actually becomes your z double dot plus omega n square z. Here you are going to have 3 beta is equals to 0, isn't it? Using 1 and 2 comma, this is what I got. This is my new equation. Okay, see, it is very important that you people understand that there are two things. One is a fixed point and another is a periodic solution. So if I have a fixed point solution, what is going to happen? If I have a fixed point solution, it is going to satisfy the differential equation. However, the system is going to be stable at that point. Whatever the system behavior is, it is going to come back to the fixed point or go away from that fixed point. Whatever we are talking is in reference with the fixed point. But in this case, we are actually considering a periodic solution, and whatever we are talking about the perturbation, about the stability or instability, we are talking about that periodic solution. And that solution is actually satisfying this equation. See, from the equation also you can see that it is anyways going to show some behavior, be it periodic, quasi-periodic, whatever it is, but it is going to be show a solution other than that of a fixed point because we have a forcing present in the system. Okay, so if this is my solution, I can write it like this also. Yeah, like this, I can write it like this also. So what happens in this case? Now I have two parameters here. Okay, my one parameter is this, and my second parameter is this, and third one is this one. You know that. Okay. So if you see my this parameter, what is happening to this parameter? Is it constant or is it changing with time? This is constant. This parameter is my constant. This parameter is my constant. But what about this? See, my omega n is a constant. 3 is a constant. It is a numeric value. And beta is also constant. But what about x naught? As I've already mentioned earlier also, x naught is a solution of the system which is periodic, which is changing with time. Periodic means it is changing with time. So my x naught is actually varying with time because that is what I assumed earlier. I assumed that my solution x naught could actually be given by a Fourier series or it can be given by a truncated Fourier series. In either of the cases, it is going to be changing with time. X naught can be written in terms of the Fourier series. So in this case, my x naught is actually varying with time. So what do I have? I have a system like this. Anyways, whatever the system is, what I know is that it is a parametrically excited system. This is a parametrically excited system. However, if you see, this is not the same as that of a Mathieu equation or the Hills equation. What difference exists here? The difference is that there is presence of a damping parameter as well. There is presence of a damping term as well. Okay, but that doesn't mean that it is not a parametrically driven system. It is a parametrically excited system. Okay, so what did we get from here? We get from here that if I have a damped Duffing oscillator with forcing function present, I can reduce it into a parametrically excited system if I consider a small perturbation from that of its solution x naught. Okay, and from here I can try to find out the behavior of the system. Okay, now coming on to, okay, just tell me one thing. If I have damping present in the system, will the system be stable or unstable? Anyways, the system is going to be stable, isn't it? If I have a Duffing oscillator and I have damping present in it, it is definitely a stable system. Yeah, good. It is definitely a stable system. Damping makes my system stable. Damping is sometimes damping is not good, but most of the time it is the best thing that can ever happen to a physical system, right? Damping. In any case, like if I talk about the Coulomb damping, friction that we experience, we know that friction actually resists us from walking, but friction actually helps us into walking as well. Similarly, damping actually makes a system stable. However, it results in the dissipation of the energy which is present in the system, but that also helps us in making the system much more stable, isn't it? Now, coming on to question number 5. What are the resonance conditions that may occur in a system with parametric excitation with the first three frequency modes as these? So, as I discussed earlier, for a parametrically excited system, there are three cases in which resonance can occur, right? So, for a forced system, what happens? Resonance occurs when omega is equals to omega n, right? But in case of a parametrically, that is not the case. We have three cases. Okay. So for here, for the this case, I have three modes of frequency. I have omega 1 is equals to 5, omega 2 is equals to 13, and omega 3 is equals to 21. These are my three modes of frequency. Where are these three modes coming from? We know for a continuous body, we can have infinite degrees of freedom and infinite frequencies. Okay. So we are concentrating only on three, just for example. Okay. So parametrically excited system, we have three cases or maybe two cases, and the second one has further two sub cases. Okay, so first one is what? First one is the principal parametric resonance. First one is our principal parametric resonance. So what happens in this case? Our omega, which is the frequency at which resonance will occur, will be equal to twice of omega n. In our case, n is equals to 0, not 0, 1, 2, and 3. Twice of omega n. Okay, so in that case, what are we going to have? I can have three cases. Since I have three modes, I'll have omega is equal to twice of 5, which is going to give me 10. Then I'll have omega is equals to twice of 13, which is going to give me 26. And then I can have omega is equals to twice of 21, which is going to give me 42. These are all in hertz. Okay, so these are the principal parametric resonance which can occur at all these frequencies. Okay, now coming on to the second case. Okay, I have written one here. Second case, which is what? Combination one, if you remember. Okay, first one was the this parametric resonance, principal parametric resonance, and the second one was my combination. And the combination was further divided into two categories. Okay, so combination. One was my sum, in which I was doing the sum of the frequencies, and the second one was where I was doing the minus of the frequency. Okay. So talking about the sum, what can I have? Omega is equals to omega m plus omega n. What do I have to do? I have three frequencies. I have to sum these. Okay. So what can I have? I can have omega is equals to omega 1 plus omega 2. What is it going to give me? 5 plus 13, which will be 18 hertz. Then I can have omega is equals to omega 1 plus omega 3, which is going to give me 5 plus 21, 26 hertz. I've added these twos, I've added these twos, I can add this also. We can have omega 2 plus omega 3, which will be equal to 13 plus 21, which will be what? Isn't it? So this is how you find the addition one. Now we also have a difference type, which is the subtraction, in which we take the subtraction. So what do we do there? We have omega m minus omega n. Now see, I have three modes: 5, 13, 21. Okay, so for these 5, 13, and 21, if I'm taking a difference, obviously I have to subtract the lower frequency from the higher one. Can the frequency have a negative value? It can never have a negative value, no. It is always going to be positive. So I have to keep in mind is that I subtract the smaller value from that of a greater value. So what can I have? I can have omega 3 minus omega 2. What is it going to give me? It will give me 21 minus 13, which is going to be 8 hertz. Then I can have omega as omega 2 minus omega 1, which will be 13 minus 5, which is going to be what? Okay, nice. It is also going to be 8 hertz. And then I can have omega as omega 3 minus omega 1. And what is this going to give me? This is going to give me around 16. So these are my frequencies which are of importance. Okay, so these frequencies is what I have to be cautious about. Okay, so this is how you are going to find the resonance condition. You have three types. Essentially, you have two types. The second one is of some type and difference type. So the first one is the principal parametric resonance, in which you take twice of that of the whatever the frequency is of a particular mode. And in the second case, you take the combination of different modes. Like I have three modes, I've taken combination of 1, 3, 1, 2, 2, 3, like that. Okay, and these combinations can have summation also and this difference also. Okay, the only thing you have to keep in mind is that while taking the difference, it should never come out to be positive. So you have to subtract the smaller value from that of a higher value. Okay, so I hope that this is clear. Okay, now I have this question number 6. If the eigenvalues of a monodromy matrix is -1 and the steady state response is periodic with time period 16, then the time period of the parametric excitation is. So if you people have gone through the classes, this question is very easy, but I'm considering that it is a bit tough question. So I'll be first explaining the theory briefly, and then after I explain the theory, then we'll take the question. Okay. So from where is this monodromy matrix coming from? What is this eigenvalues and everything? So if you people remember, I've talked about the stability of a 2 degree of freedom system in which we had x dot is equals to something, a linear combination of x and y dot is equal to a linear combination of x and y, and from there we were actually calculating a matrix, and then from that matrix we were actually calculating the lambda, where lambda was my eigenvalue, and by using those eigenvalue I was telling about the stability of the system. Okay, likewise for the non-linear system I was computing the Jacobian, and then by the Jacobian I was finding out about the stability of the system of or stability of a particular fixed point. In case of a parametrically excited system, we actually use a theory which is known as the Floquet theory. Okay, so the Floquet theory basically tells about that whether a particular, I mean, solution is stable or unstable, whether the system is stable or unstable. Okay, so what do we do in a Floquet theory? So firstly, I'll assume that I have a Floquet theory. Okay, so firstly, I assume that I have a system like this. X naught is equals to, okay, not x naught, I'll have x, okay, u double dot is equal plus p1 of t into u dot plus p2 of t into u is equals to 0. Okay, so I assume that this is my equation. Okay, you know that we take an equation, ideal equation, and then we try to find out how the system is going to behave. Okay, so this is my equation. Now I have to find out that how the system is going to behave, whether it is stable, whether it is unstable, or whatever it is. So if you see that this equation I can convert into two first order differential equations. This is a second order differential equation. I can convert it into two first order differential equations. Correct? I think that is clear. So if I have a two first order differential equations and if I have two solutions, if you remember, I have discussed it in the previous live session also, that for a two degree of freedom system, if I have two solutions, I can find any two solutions. Okay, then I can write the general solution as the linear combination of those two solutions. If you remember, this was the approach. For a two-dimensional system, if I have two solutions, then I can write the general solution as the linear combination of those two solutions. Similar is going to be applied in this also. If I have two solutions, I can write the general solution as a combination, linear combination. Now, the first thing that is to be kept in mind is that your my P1 and P2, whatever it is, general my P is actually periodic. My P of I is actually periodic with capital T. Capital T is my time period. So my capital T plus T is equal to, this means that it is periodic, right? Whatever the response is at T, the response is the same at T plus capital T, where my capital T is the time period. So we say that it is periodic with capital T. Okay. So for example, if I want to find out that what is the solution. So let us assume that I have two solutions, U1 and U2. U1T and U2T are my two solutions. So I can write a general solution. I can write a general solution as C1 of U1 of T plus C2 U2 of T. This is my general solution. So this U of T is a general solution, right? So this general solution, this T can have any value. It could be T, it could be T plus capital T, it could be T plus twice of capital T. So let us assume that I want a solution for after a one time period. Okay. So what is going to happen? See, if I assume that I want to find this, okay, I'll just replace in the main equation. Let's see what happens. So in the main equation, if I put, this is going to be U of T plus capital T plus P1 of T plus capital T into U dot of T plus capital T plus P2 of T plus capital T into U of T plus capital T is equal to 0. So if you remember, my P is periodic. I don't know whether my U is periodic or not, but I know that my P is periodic with time capital T. So then I'll have U double dot of P1 of T. See, now U of T plus capital T is actually satisfying the main equation. If you see clearly, this was my main equation. Okay, U was the solution which was satisfying this equation. Now I have replaced it with U of T plus T. I have taken a difference of time and I have seen that since my P1 and P2 are periodic, my U of T plus T is actually satisfying the main equation. So if this is satisfying the main equation, what does it mean? It means that my U T plus capital T is actually a solution of my equation, correct? This means that U of solution of the equation, let us say 1. Okay, so if this is a solution, it means that U of T plus capital T, I can write it as a linear combination of U1T and U2T. U1T and U2T are two solutions. u of t plus capital T is another solution, and we know that I can write any solution as a linear combination of two solutions that I know. So I can write it that way. Right. So now what can I write? I can write that my u 1 of t plus capital T is equal to, let us say that initially I assumed C1, C2. For here I am assuming A11, A12 because we'll be converting it into a matrix form and it will help in writing the matrix. So I can write it as A11 U1 of T plus A12 U2 of T. And I can write another solution like this, A21 of U1 of T plus A22 of U2 of T. I can write it. Right. Now, if you see that, is it a fundamental solution? When I say fundamental solution, what I mean is that if you remember for a two-dimensional system, we talked about the eigenvalues and eigenvectors. We had any two solution, we can have any two solutions, but we try to find out a solution, okay? And then we prefer going into the eigen direction and finding a solution corresponding to the eigenvalues. Why? Because those two solutions were actually independent of each other, right? Those two solutions were actually independent of each other. Okay. So here if you see, if I can anyway write some solution in such a way such that we get a fundamental solution. By fundamental solution, I mean that the matrix that I'm getting over here, like if I want to write, I can write it in matrix form like A11, A12, A21, A22. And then here we are going to have U1T, U2T. Now we can see that this matrix is having all the four terms. Okay. But what if I now go into the eigen solution? I go into the eigen direction. What is going to happen? Then I can convert this matrix into a diagonal matrix, right? And the off diagonal terms, which is my A12 and A21 are going to be 0. Isn't it? Then it can happen. Then I'm going to have a fundamental solution. So if I assume that for a fundamental solution, let us assume that for a eigen vector v1, v2, I can have v1 of this is equal to A11 of, not A11, actually the matrix is going to change, so we can write it as lambda 1 into V1 of t. Then we can write V2 is equals to lambda 2 into V2 of t. Okay, so what are these? These are my fundamental solutions. Okay, these are my fundamental solutions, or we can say the normal solution. Okay, and this is also known as the normal form of Floquet solution. Okay, so this was my solution. This is also my solution. This is also my solution. The only difference is that this is given in a fundamental form in the eigen by the use of the eigenvalues. Okay, by eigenvalues I can find the two solutions which are independent. The off diagonal terms are going to be 0. Okay. So now if I have this as solution, so if you think that my V1 of t is actually a solution at time t, and my V1 of t plus capital T is actually the solution after a time period of capital T. Similarly, if I want to know that what is the solution after a time period of 2t from small t, I want to know that what is, let us say Vi in general, here I can be 1 and 2, or for three-dimensional case, it can be 1, 2, 3. T plus 2t. What is it going to be? After twice of the time period? So we can also write it like Vi of t plus capital T plus t. Let us say that this is some t dash. So what do I know? I know that this is equal to lambda I Vi of t dash. isn't it? By using this, I can write it like this. Now, if I again write t plus capital T, what is it going to be? It is going to be lambda I square Vi of t. Following the same analogy, I can write that my Vi of t plus n times of t. After n times of time period, my solution is going to be lambda I to the power n Vi of t. This is going to be my general solution after nth time period. So what do I see? I see that my Vi is actually changing with lambda I. Like the power of lambda I is increasing as my time period is increasing. Okay, my solution is Vi is equals to n times of, sorry, Vi after n time periods is equal to lambda I to the power n Vi of t. So it is actually changing with lambda I to the power n. Now, if my n tends to infinity, what does it mean? It means that the system responds after infinite time. So if you see, if my lambda I is greater than 1, what is going to happen? It is going to multiply, keep multiplying. Its power is increasing. It will keep multiplying. Okay, so if that is the case, what is going to happen? If lambda I is greater than 1, I'm saying, okay, what is going to happen? N tends to infinity. My lambda I to the power infinity, what is it going to happen? It is going to go to infinity. So after infinite time period, my system has gone to infinity. What kind of a system is this? It's an unstable system. Definitely. With time, my system is going to infinity. So it's a unstable system. Okay, this means it's unstable. So what do I understand? By finding this solution, I am now able to predict that whether my system is unstable or stable depending upon the eigenvalues, isn't it? Initially, in case of a two-dimensional system when we were dealing with a force system or dam system, in case of a Duffing oscillator, what were we doing? We were actually finding the Jacobian, then we were evaluating the eigenvalues, and if my eigenvalue was negative, then I was saying that the system is stable. If eigenvalues were positive, then we were saying that system was unstable. One positive, one negative, it means it's saddle, and likewise that we were talking about. In this case, positive and negative is not what we are talking about. We are talking about whether it is greater than 1, less than 1, greater than minus 1, less than minus 1, right? So depending upon that, I can predict whether my system is unstable or stable, correct? So if my lambda I is greater than 1, this is going to infinity. Similarly, if my lambda I is less than minus 1, as my n tends to infinity, what is going to happen? My lambda I to the power infinity, it can either go to plus infinity or minus infinity. Anyways, it is going to go to infinity. It is going to go to infinity, right? See, I can have minus 2. So minus 2 into minus 2, it is going to be 4. If I talk about after the third time period, it will be minus 2 into minus 2 into minus 2, which will be minus of 8. It can have a positive value, it can have a negative value, but anyways, it is going to be infinite, and hence my system will be unstable. So I can write it by the help of a absolute function. Like what I mean is that if mod of my lambda I is greater than 1, then my system is unstable. And similarly, if mod of lambda I is less than 1, then what does it mean? It means that either my lambda I is less than 1 and it is greater than minus 1. Okay, so now it has a value with some decimal places like 0 0.9, 0 0.8, 0 0.2, 0 0.3, like that. So if my lambda I is something of this kind, and if I give power to it, what is going to happen? Like for example, if I want to calculate 0.5 into 0.5, it will be 0.25. 0.5 into 0.5, 0.25. And my 0.25 is less than 0.5. Now, if I try to compute 0.5 to the power 3, it will be 0.125, which is less than 0.25. So what do I see? I see a decreasing trend. As my power is increasing, my value is going to go towards 0 with time, isn't it? So in this case, if my n tends to infinity, my this system is going to come to 0. It will tend to 0. Anyways, it is not going to infinity, and hence my system is stable. Okay, so this is how I can find out whether my system is stable or unstable. So what do I get? So I get that if my lambda is within a unit circle, then my system is stable. If my lambda is out of the unit circle, then my system is unstable, right? And apart from that, what happens if my lambda is equal to +1 or -1, which is the transition case? What is going to happen to the system, whether it is stable, whether it is unstable, or whatsoever is going to happen? So I'll first take if lambda I is equal to 1. And we'll see that how the system is actually changing with time. So, for example, if I want to find out Vi of t plus capital T, what is going to happen? 1 to the power 1 Vi of t, which is going to be Vi of t only. Okay, fine. Vi of t plus 2t, 1 to the power 2 Vi of t, which is going to be Vi of t. So what am I seeing? I'm seeing that my response is periodic. My response is periodic. If you remember that in case of an unstable system, what was happening? My response was going to infinity. In case of a two-dimensional system, it was going to infinity if my both the eigenvalues were positive. If my both the eigenvalues were negative, it was going to come back to the fixed point, whatever it is. And if my eigenvalues were imaginary with real part is equal to 0. It was showing periodic behavior, right? So this is the case what we have here. Okay, after a time period, it is going to have that position again, right? If it is at 3 at Vi of t, then after a time period, this is again going to come back to t. So the response is actually periodic. Okay, so and along with that, the time period is what? T, which is the same as that of the parametric excitation. My parametric excitation had a time period t, isn't it? See here, my parametric excitation had a time period of capital T. Okay, because it was repeating after capital T. Similar is the case with this as well. My Vi is now repeating itself with a time period of t. So in this case, when my lambda I is equal to 1, my system's steady state response is periodic, that too with a time period of capital T, which is same as that of a parametric excitation. Coming on to what if my lambda I is -1. So if my lambda I is equals to -1, and now if I try to see the response, now I'll have Vi of t plus capital T is equals to -1 to the power 1 Vi of t, which is equals to minus of Vi of t. Vi of t plus 2t is going to be -1 to the power 2 Vi of t, which is Vi of t. Okay. If I have Vi of t plus 3t, I'm going to have -1 to the power 3 Vi of t minus of Vi of t. And again, if I have t plus 4t, I'm going to have minus 1 to the power 4 vi of t, which is going to be this. So if you see over here, in the previous case, when it was 1, we were having a time period of capital T. But here if you see, my vi became minus vi after first time period, and it again came back to vi at after two time periods. Then after the third time period, it again went back to minus, and then again it came back to positive. So what do I see? I see that now when my lambda I is minus 1, my time period has now changed to twice of capital T. Along with that, it is also important that I keep in my mind that my response, this state response is still periodic. It is periodic, but now the time period has changed to 2 into capital T. So response is periodic with a time period capital 2 times of capital T. And you know that our T is what? Our T is capital T is actually the time period of the parametric excitation, right? So this is what I got to know from the Floquet theory. Okay, so Floquet theory helped me to find out that how my system is going to behave. Now, if I know these eigenvalues, I can know that how my system is going to behave. Anyways, let us first see what the question was. So it says that if the eigenvalue of a monodromy, what is a monodromy matrix? Anyways, this is a matrix A. Okay, I cannot call it a monodromy matrix. I'll explain you that what is a monodromy matrix in the question that will be after this. But for now, let us say that we have a monodromy matrix which is obtained by this equation only. There are certain conditions in which we obtain it and we call it the monodromy matrix. Okay. So eigenvalues of a monodromy matrix is minus 1 and the steady state response is periodic. Firstly, I know that the steady state response is periodic. It means my eigenvalue are neither going to be greater than 0 nor it is going to be less than 0. It is going to be plus 1 or minus 1. Okay. With time period 16. Then the time period of the parametric excitation. Now I know the eigenvalue is minus 1 and another response is periodic. So I can find out. I know that the time period of periodic solution is 16. Okay. So what I know is that I know that time period of the steady state periodic solution is 16. It is 16 and the eigenvalue is minus 1. So what I know is that if the time period of the parametric excitation is capital T, then the time period for the periodic steady state solution will be 2t if lambda I is equal to minus 1. And we know that lambda is equal to minus 1. So we have 2t. It is given in the question that my 2t is 16. So if my 2t is equal to 16, then my t is equal to what? 8. Right, and that is what is asked in the question. Time period of the parametric excitation is, the answer is going to be C. You know how the answer is coming out now, right? If you know that the response is periodic and the eigenvalue is minus 1, So now you can relate it. Okay, so if you have, like for example, if you know that what is the time period of the parametric excitation, then you can find out that what is going to be the time period of the steady state periodic response. Okay, I hope that this thing is clear to you all. Okay, now coming on to the question. Okay, the system given us, we have what? We have a two-dimensional system. Yeah, and we have two solutions. We have what are the response at 0 and we have what are the response at capital D, where T is the time period of parametric excitation. Okay, so I have to find out whether the system is stable or unstable. So now it is a very easy work for me. Okay, I've understood the theory, now I can do to solve it. Okay, so see, you know the formula. What was the formula? The formula was like u1 of t plus t and u2 of t plus t was equal to A11, A12, A21, A22, U1 of t, U2 of t. Now here I have t is equals to 0, right? So first is I can differentiate. Okay, I have four variables. So I'm going to have, if I have four equations, then only I can find out the values of these variables. Fine. Now first I'll try to put the numeric values that I have. Okay, so if I take small t is equals to 0, what am I going to get? I'll have u1 of t, u2 of t is equal to a11, a12, a21, a22, u1 of 0, u2 of 0, which I have the value. So this implies, now what is my u1 at capital T? 2 and u2 at capital T 6 is equals to a11, a12, a21, a22 and u1 and u2 as 0, 1, 0. Okay. So from here, what am I going to get? I'm going to get, okay, you know what? For now, I'll not use these numeric values. Okay, since I have to explain you people one thing, I'll just write u1 of t and u2 of t. Okay, so what am I going to get? I'm going to get from here that my u1 of t is equal to what? A11 and u2 of t is a21. Isn't it? So these are the first set of solution that I have. And second one is when I differentiate these equations, I can differentiate it. Okay, my A11, A12, A21 and A22. These are all what? Constants. So definitely if I apply differentiation on both, so what am I going to get? I'm going to get U dot of U1, U2 dot of T will be equal to A11, A12, A21, A22. And here I am going to get U1 dot at 0 and u2 dot at 0 and I'll just put the value so it will be 0 and 1. So what am I going to get from this? I'm going to get that my u1 dot of t is equal to a12 and my u2 dot of t will be equal to a22. These are my second set of solution. Okay, so if I use these both and if I consider this as a matrix A, I can write my A matrix as what? I can write my this A matrix as, what did I get? My A11 and A21 were U1 of t and U2 of t. and these were u1 dot of t, u2 dot of t, isn't it? This is what I got. Now this is my monodromy matrix. Okay, this is my monodromy matrix, and now if I put the numeric values, what am I going to get? u1, u2, which is 2 and 6, 2 and 6, and next I'm going to get 3 and 5. Okay, so this is the matrix that I'm going to get. Now, in order to find whether this system is stable or unstable, what am I going to do? I'm going to find the eigenvalues. So for eigenvalues, I'll have to find the determinant of a minus lambda I, which is going to give me 2. Okay, I'll just write it. 2 minus lambda, 3, 6, 5 minus lambda. Determinant of this is going to be what? 2 minus lambda into 5 minus lambda, and this is going to be minus of 18 is equal to 0. So I'm going to get 2, 5, 10, and then I'll have minus 2 lambda, then I'll have minus 5 lambda plus lambda square minus 18 is equals to 0. Lambda square minus 7 lambda minus 8 is equals to 0. So I can write it like lambda square minus 8 lambda plus lambda minus 8 is equals to 0. Lambda into lambda minus 8 plus lambda minus 8 is equal to 0. We have lambda plus 1 into lambda minus 8 is equals to 0. So I have lambda is equals to minus 1 and lambda 1 and lambda 2 is equals to 8. So these are my two eigenvalues. Okay, so how can I know whether my system is stable or unstable? Definitely by seeing how my lambda is behaving. So anyways, whatever the value of my lambda is, both my lambdas are greater than, both the lambda satisfy the condition that mod of lambda I greater than 1. This means that the system is, this means that my system is unstable. Okay, so this is how you are going to know whether the system is stable or unstable. Okay, now coming on to the eighth question. So the eighth question says that the Floquet multiplier of a system with response at t is equals to 0 and t is equals to capital T given as follows is. So the first question is, what is a Floquet multiplier? Right, we know eigenvalues. I mean, we can find the solution by eigenvalues. So what is the use of a Floquet multiplier? However, this Floquet multiplier thing is not that much of a, I would say, important thing. But if you know, then that is nice. So, however, if you can find the eigenvalues, you can find the stability of the system. Okay. So here also, my capital is T is the period of parametric excitation. Okay. So firstly, what is a Floquet multiplier? So I'll not get into explaining you the derivation. Okay, that has been done very thoroughly in the lecture videos. Okay, so if in case you have any doubt, you can go through the lecture video. I'll just write the formula. And this Floquet multiplier is given by gamma I, which is actually 1 by capital T. Capital T is my time period. Ln of lambda I. So this is what is my Floquet multiplier. So if you know, if I have logarithmic of some function, of some numeric value, what is going to happen? If by this value is lambda I is greater than, let us say, 1, what is going to happen? This value will turn out to be positive. While if I have the value of lambda I less than 1, it will turn out to be negative. Okay. But your question would be ki, Lambda I could be negative also. Okay, so you take out the absolute value. You take out the absolute, if, for example, my lambda I is -2, you take out the absolute value, which is 2, you put it into it and see how the system is behaving. Okay, so if my this Floquet multiplier gamma I is actually positive, then I would say that my system is unstable. While if my Floquet multiplier is negative, I would say that my system is stable. Okay, so if I want to know that whether my Floquet multiplier is positive, negative, one positive, one negative, what am I going to do? I'm going to use the same way that I used to solve the previous question. I would use the equation this u of t plus capital T, u1 of u2 of t plus capital T, a11, a12, a21, a22, u1 of t. I'll just write 0, okay, because the people know that we have the initial condition as 0. So I'll just put the values from the question which I have. So I'll have -4, then I have 3, 1, 0. So this is going to give me my A11 as -4 and my A21 as 3. Similarly, if I take the velocity component and then I try to write with the help of that, I'll have u1 dot at 0 plus capital T, u2 dot at 0 plus capital T will be equal to A11, A21, A12, A22, u1 dot at 0, u2 dot at 0. Okay, and I'll just put the conditions that are being given in the system, which is 1 and -2, 0 and 1. 1 and -2, 0, 1. And here again I have A11, A12, A21, A22. So from here, what am I going to get? I'll get the value of A12 as 1 and A22 as -2. Now what do I have to do? Now I have the values of the A matrix. My A matrix is what? I have 1, -2, and here I have -4 and 3. Okay, so now what do I have to do? I have to find out the eigenvalues. So for eigenvalue, I have to find out A minus lambda I determinant, which is going to be -4 minus lambda, 1, 3, -2 minus lambda, determinant of this, which will turn out to be 4 plus lambda into 2 plus lambda, because I'll take minus common from here. I'll take minus common from here, minus common from here, and then if I multiply this, is minus into minus is going to be plus. -3 is equal to 0. So I'm going to have 8 plus 4 lambda plus 2 lambda plus lambda square minus 3 is equal to 0. So I'll have lambda square plus 6 lambda plus 5 is equal to 0. So how can I write it? I can write it like lambda square plus 5 lambda plus 5 is equal to 0. So see, I prefer mathematical manipulation in order to find out the the roots of a quadratic polynomial, but you can use the formula also, minus b plus minus under root minus b plus minus under root of b square minus 4ac divided by a to find the root. Okay, you're going to get the same value. So I'll take lambda common, I'll have lambda plus 5. Here I'll take 1 as common, I'll have lambda plus 5 is equal to 0. So, okay, fine. Yes, 2a. So lambda plus 1 into lambda plus 5 is equal to 0. So from here, what am I going to get? I'm going to get the value of the eigenvalues as lambda 1 is equal to minus 1 and lambda 2 is equals to minus 5. Okay. So what do I see? That my both the eigenvalues are negative. Okay. Both lambda are negative. Okay. But this negative value of lambda is not going to help me whether my system is stable or unstable. So what am I going to do? I'll either see, you can from here also predict whether the system is stable or unstable, but the question is asking about the Floquet multiplier. So as we know that a Floquet multiplier gamma I is going to be what? It is going to be 1 by capital T into ln of lambda I. So I have gamma 1 as, I'll find the absolute value. So I'll have gamma 1 as 1 by capital T into ln of 1, and second one is going to be 1 by capital T ln of 5. Anyways, both are going to be what? Both are going to be positive. So the answer to my system would be both positive. Okay, I hope that this is clear. So the Floquet multiplier is given like this. Gamma I is equal to 1 by T ln of lambda I, where lambda I is, it is the eigenvalues of the A matrix, and capital T is my period of the parametric excitation. So I have not gone through the derivation, but you should keep this thing in your mind. Okay. Also, there is one thing that I would like to mention over here, which is regarding the stability. So see, if I plot my lambda on a real and imaginary axis. So this is my real part, this is my imaginary part, and this is a unit circle. Okay, this is my unit circle. Okay, here the value is going to be 1, here the value is going to be 1, here the value is going to be iota, here the value is going to be minus of I. Okay, so for lambda, if I plot like this, or lambda, if I plot like this, lambda I should say, my system is unstable for the outer region. I'll just mark it with dots. My system is unstable for this region, isn't it? The absolute value of lambda is greater than 1. So my system is unstable for this region. My system is stable for this region. Here my system is stable. Okay. And if I talk about this line, this we know here my eigenvalues are going to be minus 1 plus 1. And here I need to find out whether what kind of a behavior it has. So this is shows transition behavior over. Okay. So if you remember this figure now, it will help you in order to analyze the stability of the system. Okay. Now coming on to question number 9. Okay. So I have taken this figure from your class itself, from the lecture. Figure taken from. Okay. So the question asks that for the Mathieu equation, the stability or instability region is plotted as shown. Which of the following is correct? See, first thing is that how do I find the stability region? Okay, so if you remember for my Mathieu equation, if this is my Mathieu equation, I can consider this as P of some T. Okay, so the Floquet multiplier, or the way the Floquet theory is telling about the stability of the system, I can use it now to find the stable and unstable region. Like it was given that in this case, this was when these both were stable and this was unstable, isn't it? Okay, so it was given in the theory, and so I tried to explain it as well, but I'll just take again that how it is happening if you want to do it on your own. So you have this equation you have, you know, the Floquet theory. Okay, so if you see here, we have the variation with omega and epsilon. What is my omega over here? My omega is nothing plus but under root of delta. This is my omega. Okay, so there is a variation between epsilon and omega. So what can you do? See, you have the equation. You can apply the Floquet theory. Okay, and if you have the response at time zero, you have the response at time capital T, where capital T is what? It is the time period of capital T, which is my time period of parametric excitation. In this case, my capital T will be what? Time period capital T is essentially 2 pi by omega, and omega is here too, so we'll have 2 pi by 2, which will be pi. I know my time period. Okay, I don't have what my system behavior is going to be at after this capital T, but what I can do is I have the equation. I have OD45. Okay, I'll apply OD45 and I have the initial condition. I can find out that what is going to be the solution after pi. One solution I can get. After that, I'll give, like if you remember, I had two initial states, 1 0 and 0 1. For 1 0, I'll simulate, and then I'll find that after time period capital T, what are going to be the my response, position and velocity. Then for 0 and 1, I'll simulate the system. I'll get what is going to be the response of my system, which is position and velocity after capital T. Once I get these two values, once I get these two values, what can I do? I can construct the A matrix. Perfect. From the A matrix, I can find out the eigenvalues. And if now I have the eigenvalue, I can know whether my system is stable or unstable. If my eigenvalue, again, if it is greater than, if absolute value is greater than 1, then my system is unstable. Absolute value less than 1, system is stable. And the lines, which are the transitions, are going to happen when my lambda is going to be plus or minus 1. Very easy. You can construct this on your own also. Okay. So this was already given. So question is that for the Mathieu equation, the stability and instability region is plotted as shown. Then which of the following is correct? I hope that it is clear to you that how we are going to plot it, because I think that it is easy. You can try it in MATLAB also. Just simulate the system. Take the initial condition as x1 at 0 as 1, x1 dot at 0 as 0, and then take another set as x2 at 0 is equals to 0, x2 dot at 0 is equals to 1. Why this? Because we want to find that by using the monodromy matrix. Okay, you can take any other initial condition also. However, this is a good approach. And simulate by using OD45 to get x1 at t, x1 dot at t, x2 at t, x2 dot at t, and x2 at t. If I get these, apply Floquet theory to find out the stability. Okay, so I think I've written it, so it will help you. Now coming on to the solution. System is unstable for epsilon 0.5 from 1.9 to, okay, sorry, I have to mention some things over here. Okay, so firstly, what is A and B? So if I talk about this line, this point is my A, this point is my B. Okay, and if I talk about this line at 1.5, this one is my C and this one is my D. Okay, I hope that this is clear to you all. Okay, so the option says that system is unstable for epsilon 0.5 from 1.9 to A. This 1.9 to A is actually the value of omega. So if you see from 1.9 to A, if I see here, and it is asking for epsilon 0.5. So if you see that my system for epsilon 0.5 here, it is what? It is stable, no? It is not unstable, it is rather stable. If my region would have been from A to B, then I can say that it was unstable because this region is where my system is unstable. This, the region which is left to this and right to this are all stable. So the first option which is saying that the system is unstable from 1.9 to A for epsilon 0.5 is incorrect. Coming on to second option. System is stable for epsilon 1.5 from C to D. Again, it is asking from C to D, this area, this line. Okay, so one for 1.5, if I see from C to D, what is actually happening? From C to D, it comes inside the region of instability. Okay, so my system is actually unstable and not stable. Coming on to option C, system is stable for epsilon 0.5 from 1.9 to A. Yes, this is the correct option. See here, in this region, system is stable, isn't it? And coming on to the fourth option, system is unstable for epsilon 1.5 from C to D. Yes, but this region is unstable. So this is also correct option. But my question is that what is this graph about? How is this going to help me? What is the point of these kind of graphs? So see, if you have a system that can be governed by the Mathieu equation and you have the variation of epsilon and omega, what can you do is that from these kind of a graph, you know that what is going to be the behavior of my system. Okay, like for example, if I say that my epsilon is 1.5 for an instant, and now I am trying to give it a frequency of omega which is 2. My natural frequency of the system is 2. What is going to happen? It is in the instability region. The system is going to go to infinity. The system is not at all stable. Right. I try that by these kind of a graph, I know that what are the stability regions of my system. And if I know that what are the stability regions of my system, I would know that what kind of a parameter value, what kind of a system I should choose. Like for example, if I talk about the natural frequency of the system, natural frequency of the system depends on what? For a linear system, it is what? It is under root k by m. K is what? K is the stiffness of the material of the spring. M is the mass. Okay, what can I do? I can change the mass. I want my system to operate between a range of, let us say, suppose 2 only. I want to operate it at 2. Okay, so I'll try to find out the value of epsilon for which this 2 can be stable. Or for example, I know that my value of epsilon is 1. So I'll try that my this, or let us say 0.5. So I'll try that my this natural frequency of the system is between the range of 1.9 to A and B to 2.5. So what can I do to change it? I can definitely change my mass. I can change the kind of a spring I'm using. I can maybe make for a fixed mass, if I want greater natural frequency, I can make the spring more stiffer. Or if I have a fixed stiffness of a spring, I'll try to make my mass smaller or maybe greater so that I can achieve the required natural frequency of the system by which my system can be operable in the stable zone instead of the unstable zone. It is always operating inside the stable zone. Okay. So these things are taken into mind for avoidance of any kind of catastrophic failure of the system. Okay. If the system is stable, the catastrophic failure cannot be very big. But if I talk about a building, high-rise building, then in that case, a catastrophic failure can lead to loss of millions of life and money. Okay, so that is why it is very important that we know what are the stable and unstable regions. Okay, coming on to the last question. Okay, so the question says that the amplitude frequency response of an artificial muscle, an artificial muscle system is shown in figure below. Which of the following is correct? Okay, so if I talk about what is this amplitude frequency response. So the thing is that my system is, if I give some omega to the system, okay, what is going to happen? System is going to oscillate. Now, in case of these kind of a system, if I increase the omega, what is going to happen? The amplitude of the oscillation is going to increase, right? So if the amplitude of oscillation is going to increase, so then what is going to happen? Right. Like if you remember, in case of a spring mass system, spring mass damper system, my amplitude of oscillation was maximum when my omega was equal to the natural frequency of the system. Right? And it was a very straight graph like this. The peak was at omega is equal to omega n. This is my omega is equal to omega n. This is omega, this is amplitude. And my graph was something like this. Right, I had an infinite amplitude when omega was equal to omega n. This was for a linear system. In case of a non-linear system, that is not the case. In case of a non-linear system, this is going to bend either in this direction or in this direction, depending upon whether my system is hardening or softening. Okay, so if this is the case, what is happening, then how do I know that what is the operational zone of my system? Right, it is very important that I know that what is the operational zone. Now, by operational zone, I mean that what should be the value of omega. So, see if you see here that now this figure was also taken from, this was also taken from the lecture itself. So, if you see, this blue one is my stable solution and this red one is my unstable solution. Okay, so what is happening to the system? If I see that for -5, let us say sigma, detuning parameter. So sigma can be positive or negative, and sigma is 0 when omega is equal to omega n. So we write as omega is equal to omega n plus sigma. So that we know that what is the variation of amplitude greater than and less than that of omega n. Okay. So let us say for sigma -5, what can I see? Let me use green color for this. What can I see? I see that there are two stable solutions. One is this and the other one is this. Okay, A and B. Now my A is equal to 0. Anyways, B is not equal to 0. So if this is an artificial muscle, what do I want? I don't want that if I give any kind of a actuation to the system with a frequency, whatever I say, then I don't want that it remains at A is equals to 0. I don't want that it is not even actuating. Anyways, A is equals to 0 is a trivial solution. So I'll talk about a non-trivial solution. So I want it to actuate. So for B, it has an actuation, it has some amplitude. Okay. Now if I see that if I keep increasing my sigma, my this is increasing like this. It is going like this. Okay. With the increase of omega, my oscillation amplitude is also increasing. Right? When I'm increasing the omega. Now if I talk about that if I start from here, what is going to happen? And if I start decreasing the omega. Here also I'll see that it is following this path, increasing omega. Okay, but if you see that as soon as it reaches the point P, and if there is this very, very infinitesimally small decrement in the value of omega from point P, this is going to jump like this to what? To the position A. And after that, further decrement of omega is going to make the system to follow this. Decrement in what? My amplitude of oscillation. So the question is asking me that what should I be using for the actuation of the muscle? Okay, so first thing is that if I talk about an artificial muscle, how is my muscle working? Okay, if I like the movement of my finger, if I see, it is a gradual movement, either it is a very fast movement. Okay, but if I am moving it gradually, okay, so I want it to move gradually, no? It should not be like if I'm moving it gradually and there is an abrupt shift like this. Okay, if I'm walking very slowly, and there is an abrupt change in my this position of leg. What is going to happen? I may fall down. Definitely, I am going to fall down. Right. So that is why if I follow the backward sweep, though up till P, I am achieving that with the decrease of omega. I am seeing that my amplitude is increasing, but at point P, even a small difference, very infinitesimally small change in omega can lead to abrupt change in the amplitude. Okay, this can actually cause some kind of a failure into the system. Or anyways, instability is going to take place. Okay, so it is not preferable that we take up this kind of a jumping. Okay, if my system is stable, if it is capable of making it stable, then we can maybe use this, but it is not generally preferable. So if I talk about the solutions, it says that the muscle should be used by sweeping up the frequency. Yes, I can use the muscle by sweeping up the frequency. Definitely I can, because the increment is always going to increase the amplitude of oscillation. Okay, up till what I can see in the graph. So it will increase and I can use it because there is no abrupt change in the system. Okay, so this is going to be the correct answer. Now coming on to B, the muscle should be used by sweeping down the frequency. I would say that this answer is incorrect. Although if it was mentioned that up till point P, it could have been a correct answer, but it has not mentioned anything about P, so this is going to be a wrong answer. If it mentions that there is that up to the frequency, point P, then I can use it definitely because up till there I'm avoiding any kind of instability in the system. The muscle should be used by sweeping both up and down of the frequency. Again, here it is not mentioned the specific points, so I would say that the answer is incorrect. But if the points would have been mentioned, I can actually change my answer. So the correct answer of this question is going to be A. Okay, I hope that this thing is clear to you. So we talked about parametrically excited system, right? And how can we deal with parametrically excited system? And if I talk about, if I give us some brief understanding of how a parametrically excited system is actually working, so many things present in the I would say a natural uh, this earth in the nature, they are in some way parametrically excited. We are changing maybe the mass or maybe anything, or maybe if there is some kind of an interaction like electromechanical system or magnetomechanical system, they are going to have some kind of a parametric excitation. Or I would say that there is a dependence of the parameter on time. So for that kind of a system, it is very essential that we understand that how the parametric system is actually working. Okay, like for a Duffing oscillator, now it has become, I'm hoping that it has become very clear and crystal clear to you all after solving so many questions and taking different type of problems. It is very clear that how are we going to tackle the Duffing oscillator kind of an equation of forced system. Okay, either numerically, analytically, or what kind of a behavior it can show. Similarly, it is also important that we know that how the parametric system is actually working and how the parameters are actually influencing the system behavior. Like you saw that the resonance response, it changes significantly in case of a parametrically excited system rather than a forced system, right? So this is it for today's live session, and it would these questions are going to help you in order to solve the assignment problems. And if you have any doubt, you can ask or ask in the later on live sessions. So that is it. Thank you.
Thank you, madam.
Okay. Thank you. I'll end the meeting now.